Hello there. My name is Alara, and welcome to the Late Night Science Channel. Tonight, we're going to talk about something you use every single day, but probably never think about. Something so fundamental to existence that without it, nothing could move, nothing could change, nothing could be. And yet, despite using it constantly, despite building technology around it, despite photographing it and measuring it, we still don't know what it actually is. I'm talking about space-time. If you enjoy these peaceful journeys into the mysteries of science, go ahead and give this video a like or subscribe. It really helps us continue making these relaxing explorations. Now, let's begin. Close your eyes for a moment, or just let your gaze soften. Take a breath. You're lying in bed right now, and around you is space. The space between you and the walls, the space your room occupies, the space stretching out beyond your window into the night. And as you lie there, time is passing, seconds ticking by, minutes flowing forward, carrying you from this moment into the next. Space and time feel like the most obvious, most basic things in the universe. But what if I told you that space and time aren't separate things at all? What if they're woven together into a single fabric? A fabric that can bend and stretch and ripple like the surface of a pond. And what if I told you that despite knowing this for over a century, despite using this knowledge to navigate with GPS and detect black holes and understand the cosmos, we still don't know what this fabric is actually made of? That's the mystery we're going to explore tonight, not with urgency or stress, but gently, peacefully, letting the wonder of it wash over you as you drift towards sleep. Because some mysteries aren't meant to be solved in one night. Some mysteries are meant to be carried with you into dreams. Let's start at the beginning, with a man sitting in a patent office in Switzerland. The year was 1905. Albert Einstein was 25 years old, working a regular job examining patent applications for electromagnetic devices. He wasn't a professor yet, didn't have a laboratory, didn't have access to expensive equipment or a team of researchers. During the day, he reviewed patents. At night, he thought about the universe. And in that year, 1905, he published 4 papers that would change everything. One explained Brownian motion, the random jiggling of tiny particles suspended in water, and proved that atoms were real. Another explained the photoelectric effect, showing that light comes in little packets of energy called photons, helping to establish quantum mechanics. And 2 papers introduced what we now call special relativity. Special relativity sounds complicated, but the core idea is actually simple. Einstein realized something that seems impossible at first. The speed of light is always the same, no matter how fast you're moving. Think about it like this. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the ground watching you would see the ball moving at 120 kilometers per hour. The speeds add up. That makes sense. That's what we expect from everyday experience. But light doesn't work this way. If you are on a spaceship moving at half the speed of light and you shine a flashlight forward, you might think the light would move at 1.5 times the speed of light from the perspective of someone watching you from outside. But it doesn't. The light moves at exactly the speed of light, about 300,000 kilometers per second, both from your perspective and from the perspective of someone watching you from outside. The same speed, always. How can this be? How can light be moving at the same speed for both observers when one observer is already moving at half the speed of light? Einstein's answer was radical, revolutionary, beautiful. Space and time adjust to keep the speed of light constant. If you're moving very fast, Time literally runs slower for you from the perspective of someone standing still, and distances in the direction you're moving actually contract, they shrink. These aren't optical illusions, they're not tricks of perception, they're real physical effects. Space and time are not absolute, they're relative, depending on your motion. The only thing that's absolute, that's the same for everyone regardless of how they're moving, is the speed of light. This was shocking in 1905. It overturned centuries of assumptions. Isaac Newton had built physics on the idea that time flows the same for everyone, that a second is a second no matter where you are or how fast you're moving. Einstein showed that wasn't true. Time is flexible, space is flexible. They bend and stretch depending on your motion. Let yourself imagine that for a moment. If you could build a spaceship that travels at 99% of the speed of light, and you took a journey to a star 10 light years away and back, from your perspective on the ship, the journey might only take a couple of years. But when you returned to Earth, 20 years would have passed. Your friends would be 20 years older. Your children might now be older than you. This isn't science fiction. This is what Einstein's equations predict, and it's been confirmed by experiments countless times. We've tested this with particles in accelerators. Unstable particles that normally decay in microseconds live much longer when they're traveling at nearly the speed of light. We've tested it with atomic clocks on airplanes. When you fly an atomic clock around the world and compare it to an identical clock that stayed on the ground, the traveling clock shows less time has passed. The difference is tiny, just a few nanoseconds, but it's measurable, and it matches Einstein's predictions exactly. As you lie there, breathing slowly in and out, think about what this really means. There's no universal now, no cosmic clock ticking at the same rate everywhere. When you say something is happening right now on a distant planet, that statement has no absolute meaning. Different observers moving at different speeds would disagree about what right now means. Time is not a river flowing at a constant rate for everyone. It's more like a fabric that can stretch and compress depending on how you're moving. But Einstein wasn't finished. Special relativity only dealt with objects moving at constant speeds. It didn't handle acceleration. It didn't handle gravity. And gravity was a problem because Newton's law of gravity had worked brilliantly for over 200 years. You could use it to predict the motion of planets, the trajectory of cannonballs, the orbits of moons. It was one of the most successful theories in the history of science. But Einstein realized it couldn't be completely right. Newton's gravity worked instantly. If the sun suddenly disappeared, Earth would immediately fly off into space. According to Newton's equations, the gravitational pull would vanish instantly across 150 million kilometers of empty space. But Einstein had just shown that nothing can travel faster than light. No signal, no force, no information can cross space instantly. If the sun disappeared, it would take about 8 minutes for the light to stop reaching Earth. That's how long light takes from the sun to us. And Einstein realized gravity couldn't work any faster than light either. There had to be a delay. Something had to carry the gravitational force, and whatever it was couldn't move faster than light. This led Einstein to what he called the happiest thought of his life. It came to him in 1907. He was sitting in his office at the patent office, thinking about gravity, when he imagined a worker falling off a roof. While the worker is falling, Einstein realized, the worker doesn't feel their own weight. They're weightless. They're in free fall. If they dropped a hammer while falling, the hammer would float next to them, falling at the same rate. They wouldn't see the hammer accelerate away or toward them. It would just hover there in midair from their perspective. This seems obvious now. We've all seen footage of astronauts floating in the International Space Station. But Einstein realized something profound. The worker falling off the roof and the astronaut floating in space are experiencing the same thing. They're both in free fall. The astronaut isn't actually floating in zero gravity. They're falling toward Earth, just like the worker, but they're also moving sideways fast enough that they keep missing Earth. They're in orbit, continuously falling, but continuously missing the ground. And that's why they feel weightless, not because there's no gravity, but because they're in free fall. Einstein realized that being in free fall is indistinguishable from being in empty space with no gravity at all, and being in a rocket accelerating upward is indistinguishable from standing on the surface of a planet feeling gravity pull you down. You can't tell the difference. If you're in a closed room with no windows, there's no experiment you can do to determine whether you're sitting on Earth's surface, feeling gravity, or sitting in a rocket in deep space, accelerating upward. The effects are identical. This is called the equivalence principle. Acceleration and gravity are the same thing. They're equivalent. They're the same thing. And this was the key insight that led Einstein to his theory of general relativity. If acceleration and gravity are the same thing, and if special relativity says that acceleration affects space and time, then gravity must also affect space and time. Gravity must curve space and time. Let that sink in as you breathe slowly. Gravity isn't a force pulling objects together. Gravity is the curvature of space-time itself. It took Einstein another 8 years to work out the mathematics. From 1907 to 1915, he struggled with the equations. He learned advanced mathematics he'd never studied before. He made mistakes, published wrong results, corrected them, and tried again. It was the hardest work of his life. He later said the final year, from late 1914 to November 1915, was the most exhausting and demanding time of his entire career. But in November 1915, he finally got the equations right. He published his theory of general relativity, and physics would never be the same. General relativity says that mass and energy curve spacetime, and objects moving through curved spacetime follow curved paths. That's what we experience as gravity. It's not a force pulling objects together. It's objects following the straightest possible paths through warped geometry. Those paths just happen to curve because the geometry itself is curved. The classic analogy is a rubber sheet. Imagine stretching a flat rubber sheet taut. If you place a heavy ball in the middle, it creates a dip, a curve in the sheet. Now, if you roll a smaller ball across the sheet, it will curve toward the heavy ball, not because the heavy ball is pulling it, but because the sheet itself is curved. The small ball is trying to roll in a straight line, but the curved sheet forces it to follow a curved path. This is what mass does to spacetime. The sun, with its enormous mass, curves spacetime around it. Earth is trying to move in a straight line through space, but the curved spacetime around the sun forces Earth to follow a curved path. That curved path is Earth's orbit. We experience this as the sun's gravity pulling on Earth. But from Einstein's perspective, there's no pull at all. There's just Earth moving through curved spacetime. Now, this rubber sheet analogy is helpful, but it's also misleading in some ways. The rubber sheet is a two-dimensional surface curving in three-dimensional space. But spacetime is four-dimensional, 3 dimensions of space plus 1 of time, and it's not curving in some higher dimensional space. It's curving in on itself. This is hard to visualize because we can't picture four-dimensional geometry. Our brains evolved to understand 3 spatial dimensions, not four-dimensional spacetime. Also, the rubber sheet analogy makes it look like gravity is pulling the balls down, but that's our Earth gravity doing the pulling in the analogy. In real spacetime, there's no external force. The curvature itself is gravity. Objects follow geodesics, which are the straightest possible paths through curved spacetime. A planet orbiting a star is following a geodesic. It's moving in what it thinks is a straight line, but because spacetime is curved, that straight line curves back on itself, creating an orbit. As you rest there, feeling the weight of your body against the bed, that's not Earth pulling you down. That's you trying to follow a straight path through spacetime, and the ground getting in your way. The ground is pushing up against you, preventing you from following your natural geodesic through curved spacetime. If the ground suddenly disappeared, you'd fall, not because gravity started pulling you, but because you'd finally be free to follow your natural path through spacetime. Einstein's theory was beautiful. It was elegant. It explained everything Newton's gravity explained, but in a more fundamental way. And it made new predictions that Newton's theory couldn't account for. One of the first successes was explaining the orbit of Mercury. Mercury, the closest planet to the Sun, has an orbit that's slightly off from what Newton's equations predict. The point where Mercury is closest to the Sun shifts very slightly with each orbit. This is called the precession of Mercury's perihelion. Astronomers had known about this for decades and couldn't explain it. Some thought there might be another planet closer to the Sun than Mercury, pulling on it and causing the shift. But Einstein's equations predicted the exact amount of precession without needing any extra planets. Spacetime was curved more strongly near the Sun, and that extra curvature explained Mercury's strange orbit perfectly. But the real test came in 1919. Einstein's theory predicted that light would be bent by gravity. More specifically, starlight passing near the Sun would be bent by the Sun's curved spacetime. The stars would appear to shift position slightly when the Sun was nearby. But you can't normally see stars near the Sun during the day. The Sun is too bright. It drowns out the starlight. You can only see stars near the Sun during a total solar eclipse, when the Moon blocks the Sun's light. On May 29, 1919, there was a total solar eclipse. Two expeditions, one led by Arthur Eddington traveling to the island of Príncipe off the coast of West Africa, and another traveling to Sobral in Brazil, photographed stars during the eclipse. They measured the positions of stars near the Sun and compared them to the positions of the same stars photographed at night when the Sun wasn't nearby. The stars had shifted. Light had been bent by the Sun's gravity, exactly as Einstein predicted. The measurements matched Einstein's equations. When the results were announced in November 1919, Einstein became an overnight celebrity. Newspapers around the world ran headlines about the eclipse results. Einstein's face appeared on magazine covers. He was invited to give lectures everywhere. He went from being a respected physicist to being the most famous scientist in the world. By 1922, everyone in the physics community agreed Einstein had solved gravity. The problem was closed. The theory was complete. Except it wasn't. Einstein's equations were beautiful, but they were also difficult to work with. Most physicists in the 1920s and 30s couldn't solve these equations except in very simple cases. One of the simplest solutions was found by Carl Schwarzschild in 1916, just a few months after Einstein published his theory. Schwarzschild was a German physicist serving in the German army during World War I. Despite being on the Russian front, dealing with the harsh conditions of warfare in 1916, he found time to work on Einstein's equations. He solved them for the simplest possible case, a perfectly spherical, non-rotating mass sitting alone in empty space. The solution worked. It described how space-time curves around a star or planet. But Schwarzschild noticed a strange thing in the mathematics. At a certain distance from the center of the mass, the equations seemed to break. They gave infinite values. They stopped making sense. This distance became known as the Schwarzschild radius. For the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it's about 9 millimeters. These numbers seemed meaningless at the time because the Sun is much larger than 3 kilometers across. It has a radius of about 7,300 kilometers.
Earth is much larger than 9 millimeters. It has a radius of 6,300 kilometers. The strange behavior in the equations only appeared deep inside the physical mass, where the vacuum solution didn't really apply anyway. So most physicists ignored it. It was just a mathematical quirk, an artifact of the idealized spherical solution, nothing to worry about. Schwarzschild himself died just a few months after publishing his solution. He contracted an autoimmune disease while serving on the Eastern Front and died in May 1916 at the age of 42. He never knew how important his solution would become. For decades, the Schwarzschild radius remained a mathematical curiosity. Physicists knew about it but didn't think it had any physical significance. Einstein certainly wasn't worried. In fact, he actively disliked the implications. If you somehow compressed a mass smaller than its Schwarzschild radius, the equations predicted something bizarre. Spacetime would curve so strongly that nothing could escape, not even light. The object would become what we now call a black hole, and at the very center, all the mass would collapse to an infinitely small point, a singularity, where the curvature of spacetime became infinite and the laws of physics broke down completely. Einstein thought this was absurd. He believed it revealed a limitation of the theory, not a prediction about reality. He wrote papers in the 1930s arguing that nature would never allow such a thing to happen. He believed that matter would resist being compressed that much. There would be some force, some pressure, some quantum effect that would prevent collapse. Beyond the Schwarzschild radius, the singularity was a mathematical artifact, not a real physical possibility. It was like dividing by zero in an equation. You get infinity, but that doesn't mean infinity exists in nature. It means you've pushed the equation beyond its domain of validity. Most physicists agreed with Einstein. The idea of a star collapsing so completely that it disappeared from the universe seemed ridiculous. Stars are held up by pressure. Hot gas pushes outwards. This pressure balances gravity's inward pull. When a star runs out of fuel, it cools down, pressure drops, and gravity takes over. But surely there would be some force that would stop the collapse. Maybe the pressure of electrons pushing against each other, a quantum effect called degeneracy pressure. This is what holds up white dwarf stars. Or maybe the pressure from neutrons, which holds up neutron stars. Something would stop the collapse. It had to. But in 1939, J.R. Robert Oppenheimer, who would later lead the Manhattan Project, and his student Hartland Snyder, published a paper that changed everything. They modeled a massive star running out of fuel, no longer able to support itself against its own gravity. They showed mathematically that for their idealized model, there was nothing that could stop the collapse. No pressure, no force was strong enough to halt it once it started. The star would shrink past its Schwarzschild radius and keep shrinking until it became a singularity, a point of infinite density where the laws of physics broke down completely.
Einstein thought this was absurd. He believed it revealed a limitation of the theory, not a prediction about reality. He wrote papers in the 1930s arguing that nature would never allow such a thing to happen. He believed that matter would resist being compressed that much. There would be some force, some pressure, some quantum effect that would prevent collapse beyond the Schwarzschild radius. The singularity was a mathematical artifact, not a real physical possibility. It was like dividing by zero in an equation. You get infinity, but that doesn't mean infinity exists in nature. It means you've pushed the equation beyond its domain of validity. Most physicists agreed with Einstein. The idea of a star collapsing so completely that it disappeared from the universe seemed ridiculous. Stars are held up by pressure. hot gas pushes outward. This pressure balances gravity's inward pull. When a star runs out of fuel, it cools down, pressure drops, and gravity takes over. But surely there would be some force that would stop the collapse. Maybe the pressure of electrons pushing against each other, a quantum effect called degeneracy pressure. This is what holds up white dwarf stars. Or maybe the pressure from neutrons, which holds up neutron stars. Something would stop the collapse. It had to. But in 1939, J. Robert Oppenheimer, who would later lead the Manhattan Project, and his student Hartland Snyder published a paper that changed everything. They modeled a massive star running out of fuel, no longer able to support itself against its own gravity. They showed mathematically that for their idealized model, there was nothing that could stop the collapse. No pressure, no force was strong enough to halt it once it started. The star would shrink past its Schwarzschild radius and keep shrinking until it became a singularity, a point of infinite density where Einstein's equations themselves broke down. Later work showed this wasn't just true for idealized models. Even with realistic equations of state describing how matter behaves under extreme pressure, massive enough stars would still collapse completely. There's a mass limit beyond which no known force can prevent collapse to a black hole. Oppenheimer and Snyder didn't call it a black hole. That term wouldn't be coined until 1967 by John Wheeler. They just described the mathematics of gravitational collapse, but the implications were clear. Einstein's own equations predicted that stars could collapse into objects from which not even light could escape, objects where space-time became so warped that it essentially sealed itself off from the rest of the universe. Einstein hated this result. He thought it showed that general relativity must be incomplete, that something was missing from the theory. But he couldn't find a flaw in Oppenheimer's mathematics. The equations were correct. General relativity really did predict these objects. Einstein died in 1955, never accepting that black holes were real. For the next couple of decades, most physicists remained skeptical. Black holes seemed too strange, too extreme. They violated our intuitions about how the universe should work. But observations started to pile up. In the 1960s, astronomers discovered quasars, incredibly bright objects in distant galaxies that were pouring out enormous amounts of energy from very small regions of space. The only explanation that made sense was that these were supermassive black holes, millions or billions times the mass of the Sun, feeding on gas and dust. The material falling into the black hole would heat up to millions of degrees and radiate energy before crossing the point of no return. And theorists were making progress understanding what black holes really meant for physics. In 1965, Roger Penrose proved a remarkable theorem. He showed that once a star collapses past a certain point, the formation of a singularity is mathematically unavoidable. It's not a matter of the star being perfectly spherical or having special properties. Any collapsing star would form a singularity. The laws of physics, as described by general relativity, literally forced it to happen. Stephen Hawking extended this work. In the late 1960s and early 1970s, working with Penrose and others, he proved that singularities are generic features of general relativity. They don't just appear in black holes. The Big Bang itself, the beginning of the universe, was a singularity, a point of infinite density and infinite curvature where time itself began. Hawking showed that if you run the expansion of the universe backward in time using Einstein's equations, you inevitably reach a singularity. There's no way to avoid it within the framework of general relativity. This was deeply troubling.
General relativity had been incredibly successful at describing gravity, spacetime, and the motion of objects from planets to galaxies. But the theory itself predicted places where it broke down, places where the equations gave infinite answers and stopped making sense. Singularities were like signs posted in the mathematics saying, beyond this point, physics doesn't work. Let yourself relax as you think about this. The universe has boundaries, places where our understanding reaches an edge and can go no further, places where the familiar rules break down and something else takes over, something we haven't yet discovered. As you breathe slowly, imagine standing at that edge, looking into the unknown, not with fear, but with quiet wonder. Then, in 1974, Hawking made another discovery that shocked the physics community. He showed that black holes aren't completely black, they emit radiation. This became known as Hawking radiation, and it came from combining general relativity with quantum mechanics in a very specific way. Here's how it works. Quantum mechanics says that empty space isn't really empty. It's filled with quantum fluctuations, pairs of particles and antiparticles that pop into existence for incredibly brief moments before annihilating each other. This happens everywhere, all the time. In normal space, far from any black holes, these fluctuations are called virtual particles. They exist for such a short time that they can't be observed directly. They borrow energy from the vacuum, exist for a moment, then pay it back by annihilating. The uncertainty principle in quantum mechanics allows this to happen as long as it happens fast enough. Usually, these particle pairs appear and disappear so quickly that they don't have any observable effect on anything large scale. But near the event horizon of a black hole, something different can happen. The event horizon is the point of no return. Once something crosses it, it cannot escape. The gravitational pull becomes so strong that you'd need to travel faster than light to escape, and nothing can travel faster than light. So anything that crosses the event horizon is trapped forever, doomed to fall into the singularity at the center. Now imagine a virtual particle pair appears right at the edge of the event horizon. One particle appears just inside the horizon, the other just outside. Normally, they would annihilate each other almost instantly, but in this case, the particle inside gets pulled in by the black hole's gravity before it can annihilate its partner. The particle outside the horizon escapes. To an outside observer, it looks like the black hole emitted a particle, but where did the energy for this real particle come from? It came from the black hole itself. When one particle of the virtual pair falls into the black hole, it has negative energy from the perspective of an outside observer. This is a strange consequence of general relativity near a black hole. The particle falling in reduces the mass of the black hole very slightly. The escaping particle carries away positive energy. The total energy is conserved, but the black hole has lost mass. Over time, this process causes the black hole to evaporate. It's slowly evaporating. The rate of evaporation depends on the size of the black hole. Smaller black holes evaporate faster. This is because the Hawking radiation temperature is inversely proportional to the mass. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvins. That's 60 billionths of a degree above absolute zero. At that temperature, it would take about 10 to the 67th years to completely evaporate. That's incomprehensibly long. The current age of the universe is only 10 to the 10th years, 13.8 billion years. A solar mass black hole would take 10 to the 57 times the current age of the universe to evaporate. But a smaller black hole would evaporate much faster. A black hole with the mass of a mountain, about 1 billion metric tons, would have a temperature of about 100 billion Kelvin and would evaporate in a fraction of a second, exploding in a burst of high-energy radiation. Tiny black holes, if they exist, would evaporate almost instantly, releasing tremendous amounts of energy.
This was revolutionary. It meant black holes aren't eternal. They have a finite lifetime. They would eventually disappear completely, evaporating away into radiation. And this created a new problem, one that has haunted physics for 50 years. It's called the information paradox. Think about it like this. Imagine you write a book, a detailed record of information, and then you throw it into a black hole. The book crosses the event horizon and falls toward the singularity. From the outside, the book is gone. All you can observe about the black hole is its mass, its spin, and its electric charge. You can't tell what fell in. A book, a rock, a star, it doesn't matter. The black hole looks the same regardless. In the 1970s, John Wheeler summarized this by saying black holes have no hair, meaning they have no features that distinguish what went into them. Now, if black holes were eternal, you might say the information is still there, locked inside the black hole forever, inaccessible but not destroyed. But Hawking radiation changes that. The black hole evaporates. Eventually, it disappears completely, replaced by a cloud of thermal radiation. Thermal radiation is random. It doesn't carry information about what created it. It's like the heat from a fire. You can't look at the heat and figure out what was burned. This means the information about the book is destroyed. The words, the ideas, the specific arrangement of particles that made up the book, all of it is gone. This violates a fundamental principle of quantum mechanics called unitarity. Quantum mechanics says that information is never destroyed. It can be scrambled, spread out, hidden in incredibly complex ways, but it's always there in principle. If you knew the quantum state of every particle perfectly, you could reconstruct the past or predict the future with perfect accuracy. Information is conserved. But Hawking radiation seemed to destroy information. The quantum state of the book is lost forever. It's as if the book was erased from the history of the universe. This created a deep conflict between general relativity and quantum mechanics. One of them had to be wrong, or our understanding of both had to be incomplete. Physicists debated this for decades. Hawking initially argued that information really is destroyed in black holes, that quantum mechanics breaks down in extreme gravitational fields. Others argued that information must be preserved somehow, that we just don't understand the mechanism yet. The paradox remained unsolved, and it became a signal that something was fundamentally wrong with our understanding of spacetime. As you lie there, breathing slowly, think about what this means. The two greatest theories in physics, the two frameworks we use to understand reality, contradict each other. One says space-time is smooth and continuous. The other says everything is discrete and probabilistic. One predicts singularities where physics breaks. The other says information cannot be destroyed. Both theories work perfectly in their own domains. GPS satellites use relativity. Computer chips use quantum mechanics, and yet they cannot both be completely right. Somewhere, at the boundary where they meet, there must be something deeper, something we haven't discovered yet, something that unifies them into a single, consistent picture of reality. Before we go any deeper into this mystery, let's pause and appreciate something remarkable. This idea we don't fully understand, this theory that breaks down at singularities and might destroy information, is something we use every single day. General relativity isn't just an abstract theory for understanding black holes and the Big Bang. It affects your life in concrete, practical ways. Let's start with the most obvious example: GPS. Your phone, your car's navigation system, any device that tells you where you are uses a network of satellites orbiting Earth about 20,000 kilometers up. These satellites constantly broadcast signals containing the exact time according to atomic clocks on board, and information about their positions. Your GPS device receives signals from at least 4 satellites, measures how long the signals took to arrive, and uses that information to calculate your position. The speed of light is constant. If you know how long a signal took to arrive, and you know it traveled at the speed of light, you can calculate how far away the satellite was when it sent the signal. With signals from 4 satellites, you can pinpoint your position in 3-dimensional space. It's simple geometry. But there's a problem. The atomic clocks on the satellites don't tick at the same rate as clocks on the ground. There are 2 effects from general relativity at work here. First, the satellites are moving at about 14,000 kilometers per hour relative to the ground. According to special relativity, time runs slower for moving objects. From the perspective of someone on the ground, the satellite clocks should be ticking slightly slower. This is time dilation due to velocity. The effect is tiny but measurable. The satellite clocks lose about 7 microseconds per day compared to clocks on the ground. But there's a second effect that's even larger. The satellites are higher up in Earth's gravitational field. They're farther from Earth's center of mass, so they experience weaker gravity. According to general relativity, time runs faster in weaker gravitational fields. From the perspective of someone on the ground, the satellite clocks should be ticking slightly faster. This is gravitational time dilation. The satellite clocks gain about 45 microseconds per day compared to clocks on the ground. That doesn't sound like much, 38 microseconds. But light travels about 300 meters in 1 microsecond. If the GPS system didn't correct for these relativistic effects, your position would be off by 11 kilometers per day. Within hours, GPS would be completely useless. Your navigation would tell you you're in the wrong city. The engineers who designed GPS knew this. They programmed the satellite clocks to tick a slightly different rate to compensate for relativity. Every GPS calculation accounts for the curvature of spacetime around Earth. Every time you use GPS to navigate, you're relying on Einstein's equations. You're using general relativity, and it works. It works perfectly. But do we understand what spacetime actually is? No, we don't. We just know how to calculate its effects. Here's another example that's even stranger. Gold. The metal gold has a distinctive yellow color. It's the only metal that looks yellow. Silver is silvery white, copper is reddish, iron is gray, but gold is yellow. Why? The answer involves relativity. Atoms absorb and emit light at specific frequencies depending on the energy levels of their electrons. For most metals, the frequency of light they absorb is in the ultraviolet range, higher energy than visible light, so they reflect all visible light and appear silvery or gray. But gold is different. Gold atoms are heavy. They have 79 protons in the nucleus, creating a strong electric field. The innermost electrons are moving very fast in this strong field, fast enough that relativistic effects become important. According to special relativity, as electrons move faster, their mass effectively increases. This changes the spacing between energy levels in the atom. For gold, this relativistic effect shifts the energy levels enough that gold absorbs blue light instead of ultraviolet. When white light hits gold, the blue frequencies are absorbed, and the remaining light that's reflected is yellow. The color of gold is a relativistic effect. Without relativity, gold would look silvery, like most other metals. The same thing happens with mercury. Mercury is the only metal that's liquid at room temperature. Why? Again, relativity. Mercury atoms have 80 protons, and the innermost electrons are moving so fast that relativistic effects make the bonds between mercury atoms weaker than they otherwise be. The atoms don't stick together as strongly, so mercury melts at a much lower temperature than you'd expect. Without relativity, mercury would be a solid at room temperature, and thermometers would work very differently. These aren't just curiosities, these are real, measurable effects of relativity in everyday materials. The universe we live in, the properties of the elements around us, are shaped by the curvature of spacetime and the flexibility of time, and we use these effects without thinking about them. Even more impressive is LIGO. The
the Laser Interferometer Gravitational Wave Observatory. LIGO is designed to detect gravitational waves, ripples in spacetime caused by violent cosmic events like colliding black holes or neutron stars. These ripples stretch and squeeze space as they pass through. The effect is incredibly small. When a gravitational wave passes through Earth, it might change the distance between 2 points separated by 4 kilometers by less than 1/10,000th the width of a proton. Let me put that in perspective. A proton is about 10 to the minus 15 meters across. 1/10,000th of that is 10 to the minus 19 meters. The LIGO detectors can measure changes in distance that small. To give you a sense of scale, if the distance between Earth and the nearest star, Proxima Centauri, about 40 trillion kilometers, changed by the width of a human hair, about 1/10 of a millimeter, LIGO would be able to detect it. LIGO detects this by splitting a laser beam, sending the two halves down perpendicular tunnels 4 kilometers long, bouncing them off mirrors at the ends, and recombining them. If a gravitational wave passes through while the light is traveling, one arm of the detector will be slightly stretched while the other is slightly squeezed. This creates a tiny change in the time it takes light to travel down each arm, and when the beams recombine, they create an interference pattern that reveals the passing wave. The first detection happened on September 14, 2015. It was the first day of LIGO's first science run after a major upgrade. The signal arrived at the detector in Louisiana at 5:51 a.m. Central Daylight Time. 7 milliseconds later, it arrived at the detector in Washington State. The signal lasted about 1/5 of a second, starting at a frequency of about 35 Hz and rising quickly to about 250 Hz before cutting off abruptly. This pattern is exactly what you'd expect from two black holes spiraling into each other and merging. The analysis showed that the two black holes each had about 30 times the mass of the Sun. They'd been orbiting each other for billions of years, gradually spiraling inward as they lost energy to gravitational waves. In the final fraction of a second, they were orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. When they merged, the collision released more energy in a fraction of a second than all the stars in the observable universe emit in the same time. About 3 solar masses worth of energy, the equivalent of annihilating 3 suns and converting all their mass directly to energy in less than a second. That energy radiated outward at the speed of light as ripples in spacetime. The event happened 1.3 billion light-years away, so the waves took 1.3 billion years to reach Earth. When they arrived, they stretched and squeezed the 4-kilometer arms of LIGO by about 1,000th the width of a proton, and LIGO detected it. The discovery was announced on February 11, 2016, after months of careful analysis to make sure the signal was real and not some instrumental artifact or noise. It was front-page news around the world. It confirmed a major prediction of general relativity that had never been directly tested. Einstein's equations predict that accelerating masses create ripples in spacetime that travel at the speed of light. We'd seen indirect evidence before. Pulsars, rapidly spinning neutron stars, lose energy at exactly the rate you'd expect if they're emitting gravitational waves. But LIGO was the first direct detection. We'd actually caught the waves passing through Earth. Since then, LIGO and its sister observatories, Virgo in Italy and Kagra in Japan, have detected dozens of gravitational wave events. Most are from merging black holes, some are from merging neutron stars. Each detection teaches us something new about these extreme objects and about the nature of gravity itself. In August 2017, LIGO and Virgo detected gravitational waves from 2 neutron stars merging about 130 million light-years away. This event was special because neutron star mergers also produce light. Unlike black holes, which are dark, neutron stars are made of normal matter, and they glow. When they merge, they create a bright explosion called a kilonova. Within seconds of the gravitational wave detection, LIGO sent out alerts to astronomers around the world. Telescopes swung into action, searching the region of sky where the signal came from. Within hours, they found it, a new bright source in a galaxy called NGC 4993. Over the following days and weeks, dozens of telescopes observed the kilonova at different wavelengths, from gamma rays to radio waves.
It was the first time humanity had observed a cosmic event with both gravitational waves and light. It was the dawn of multi-messenger astronomy. The observations confirmed something physicists had long suspected. Heavy elements like gold, platinum, and uranium are created in neutron star mergers. The collision creates conditions so extreme that atomic nuclei are smashed together and rebuilt into heavy elements. The kilonova ejected about 1/100th of a solar mass of material, much of it gold and platinum. All the gold on Earth, every gold ring, every gold coin, every gold bar in bank vaults was created in neutron star mergers billions of years ago, before the solar system formed. The gold was scattered into space, mixed with gas and dust, and eventually incorporated into the disk of material that formed the sun and planets. When you wear a gold ring, you're wearing atoms that were forged in the collision of neutron stars. Each gravitational wave detection is direct evidence that space-time is real, that it can be bent and rippled, that Einstein was right. We're not just inferring the existence of space-time from theoretical arguments, we're measuring it directly. We're watching it wiggle. But detecting gravitational waves doesn't tell us what space-time is made of. It just confirms that it exists and that it behaves the way Einstein's equations say it should. It's like detecting sound waves traveling through air. You can measure the waves, study their properties, use them to communicate and make music, but measuring sound waves doesn't tell you what air is made of. You need other experiments to discover molecules and atoms. Similarly, measuring gravitational waves tells us space-time can vibrate, but it doesn't tell us what the fabric doing the vibrating actually is. That remains a mystery. And then there are the black hole photographs. In April 2019, the Event Horizon Telescope collaboration released the first image of a black hole. It wasn't a photograph in the traditional sense, it was radio telescope data from observatories all around the world combined using a technique called very long baseline interferometry. 8 radio telescopes spread across the planet from Hawaii to Antarctica, from Spain to Chile, all pointed at the same target at the same time. They recorded radio waves at a wavelength of 1.3 millimeters, a frequency where the gas around black holes glows brightly. Combining the signals from all the telescopes as if they were parts of a single telescope the size of Earth, they achieved resolution equivalent to a telescope about 13,000 kilometers across. That's enough resolution to read a newspaper in New York from a cafe in Paris, or to see an orange sitting on the surface of the moon. The result was an image showing a ring of light around a dark circle. The black hole was in the center of the galaxy Messier 87, about 55 million light-years away. The black hole itself is about 6.5 billion times the mass of the Sun. The dark region in the center of the image, the shadow, has a diameter of about 40 billion kilometers. That's about 3 times the size of Pluto's orbit around the Sun, and it's completely dark because it's the event horizon. No light escapes from inside. The ring of light around the shadow is gas orbiting the black hole at speeds approaching the speed of light. The gas is heated to billions of degrees by friction and magnetic fields. It glows in X-rays, visible light, and radio waves.
The light we see in the image has been bent by the extreme curvature of space-time around the black hole. Some photons orbit the black hole multiple times before escaping. Some are bent just enough to reach our telescopes. What you're seeing in that image is not the black hole itself. The black hole is the dark circle in the center, the region from which no light escapes. What you're seeing is the effect of the black hole around space-time. The light from hot gas is being bent, twisted, focused by curved space-time. The image is a direct photograph of Einstein's predictions. In May 2022, the collaboration released a second black hole, this one at the center of our own galaxy, Sagittarius A star. It's about 4 million times the mass of the Sun, much smaller than the Messier 87 black hole, but it's much closer, only 27,000 light-years away. Again, the image shows a ring of light around darkness. You're looking at curved space-time. You're seeing photons that have been bent by gravity on their journey to Earth. These images are literal photographs of Einstein's predictions made visible. They're not artists' interpretations or computer simulations. They're images constructed from real data, photons that traveled from the edge of an event horizon across millions or tens of thousands of light years to reach Earth. We use this idea every single day in GPS, in the color of gold, in gravitational wave detectors, in photographs of black holes. We've built entire technologies on Einstein's framework, and that's both amazing and unsettling. It's like discovering that your house rests on an invisible foundation. You can measure how it responds to weight, you can calculate how it bends under stress, you can predict how it will behave, but the material itself remains unknown. So let's dig into the mystery. What exactly don't we understand about space-time? The answer can be broken down into 3 big questions, 3 places where our knowledge hits a wall. What is space-time made of? Let's start with the most basic question. Einstein's equations describe how space-time curves in response to matter and energy. They tell us how to calculate the curvature given a distribution of matter. They predict how objects move through curved space-time. But they don't tell us what space-time actually is. In Einstein's theory, space-time is treated as a smooth continuum. You can zoom in on any point in space, and there's always more space at smaller scales. You can divide time into smaller and smaller intervals, and there's always more time. Space and time are continuous, infinitely divisible. This works perfectly for calculations at the scales we can observe, but there's reason to believe this can't be the whole story. Quantum mechanics, the theory that describes the behavior of particles at very small scales, says that almost everything in nature is discrete, quantized, coming in chunks rather than being continuous. Energy comes in chunks called quanta. Light comes in chunks called photons. Even the spin of an electron comes in discrete values. The quantum world is fundamentally grainy, not smooth. This suggests that space and time might also be quantized at very small scales. There might be a smallest possible length, a quantum of space. There might be a smallest possible duration, a quantum of time. Below these scales, it doesn't make sense to talk about smaller distances or shorter times.
This scale is called the Planck length. It's about 10 to the minus 35 meters. To give you a sense of how small this is, a proton is about 10 to the minus 15 meters across. The Planck length is 20 orders of magnitude smaller than a proton. If you scaled a proton up to the size of the observable universe, the Planck length would be about the size of a tree. At this scale, quantum effects on space-time itself should become important. The smooth fabric of space-time Einstein described should break down into something else, something grainy, something chaotic. Physicists call this quantum foam. It's the idea that if you could zoom in far enough, space-time would look turbulent, bubbling with quantum fluctuations, constantly forming and dissolving tiny structures. But we have no direct way to probe these scales. The Planck length is so small that we can't build experiments to measure it. The energies required to probe Planck scale physics would be about 10 to the 19th giga-electron volts. The Large Hadron Collider reaches energies of about 14,000 giga-electron volts. To probe the Planck scale, you'd need an accelerator about 10,000 trillion times more powerful. So we're stuck trying to figure out what happens at these scales using pure theory, mathematics, and indirect reasoning. And there are several competing ideas, none of which we can test directly. One of the leading candidates is loop quantum gravity. This approach takes Einstein's equations and tries to quantize them directly. Instead of treating space-time as a smooth continuum, loop quantum gravity says space-time is made of discrete chunks connected in a network. Space is woven from loops, tiny loops of space-time about a Planck length in size. These loops connect to form a network, and the geometry of space-time emerges from how these loops are arranged and connected. In this picture, area and volume are quantized. You can't have an arbitrary area or volume. They come in discrete units. Space-time has a minimal possible volume, and you can't divide it any smaller. This solves some problems. It suggests that singularities might not actually exist at the center of a black hole or at the Big Bang. Instead of collapsing to an infinitely small, infinitely dense singularity, matter would collapse to a minimum volume set by quantum effects. Another approach is string theory. String theory says that the fundamental objects in nature aren't point particles, but tiny vibrating strings. Different vibrations of these strings correspond to different particles. An electron is one vibration, a photon is another, a quark is another, and one particular vibration corresponds to the graviton, the hypothetical quantum particle that would carry the gravitational force. In string theory, space-time emerges from the interactions of these strings. The strings exist in a higher dimensional space, usually 10 or 11 dimensions rather than the 4 we experience. The extra dimensions are curled up so small we don't notice them. And the geometry of space-time, the curvature we experience as gravity, comes from how the strings move and interact in this higher dimensional space. String theory is elegant in many ways. It naturally includes gravity. It unifies all the forces. But it has problems. We've searched for evidence of string theory at particle accelerators and haven't found any. And there are an enormous number of possible string theories, depending on how you curl up the extra dimensions. Current estimates suggest there might be 10 to the 500 different versions. There's also a more radical idea that's gained traction in recent years. Maybe space-time isn't fundamental at all. Maybe space and time are emergent properties that arise from something deeper, something that doesn't look like space or time at all. Some physicists have wondered if there might be a connection between quantum entanglement and the geometry of space-time. The idea is that when two particles are entangled, they might be connected by a tiny wormhole, a thread of space-time linking them. If this is true, it would mean space-time itself is woven from entanglement. The connections between distant points in space would emerge from quantum correlations between particles. Space would be an illusion, a useful way of describing something more fundamental. This is speculative, but it points to a possibility that's both exciting and unsettling. Everything we think we know about space and time might be wrong at a fundamental level. They might not be the basic building blocks of reality. They might be emergent, appearing only at large scales. The bottom line is this: we don't know what space-time is made of. We have equations that describe how it behaves. We can measure its curvature. We can detect waves moving through it. But the fundamental nature of the fabric itself remains a mystery. What happened at the Big Bang? When we run the expansion of the universe backward in time using Einstein's equations, we inevitably reach a point where the entire universe was compressed into an infinitely small, infinitely dense singularity. This is called the Big Bang singularity. It's the beginning of time, the birth of space and matter and energy all at once. But calling it a singularity is another way of saying the equations break down. At the singularity, density becomes infinite, temperature becomes infinite, the curvature of space-time becomes infinite. The mathematics stops working, and that means we don't actually know what happened. We have very good evidence for the Big Bang in a general sense. The universe is expanding. We can measure the expansion. We can see galaxies moving away from us in all directions. The farther away a galaxy is, the more its light is redshifted, which means the faster it's moving away from us. If the universe is expanding now, it must have been smaller in the past. Run the clock backward and everything gets closer together. Temperatures and densities increase. Eventually, you reach a point about 13.8 billion years ago when the universe was incredibly hot and dense. We have other evidence too. In 1964, two scientists discovered the cosmic microwave background radiation, light left over from when the universe was only about 330,000 years old. Before that time, the universe was so hot that atoms couldn't form. Light couldn't travel very far because it was constantly being scattered. But when the temperature dropped below 3,000 Kelvin, electrons and protons combined to form neutral hydrogen atoms. Suddenly, light could travel freely. The universe became transparent. Those photons have been traveling ever since, stretched by the expansion of the universe, from visible light to microwave radiation. We can detect this radiation today, coming from every direction in the sky. It's a nearly uniform glow with a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. But it's not perfectly uniform. There are tiny variations, slight differences in temperature from one direction to another. The variations are only about 1 part in 100,000, incredibly small, but they're real and they're incredibly important. These variations are the seeds of structure in the universe. Regions that were slightly denser had slightly higher temperatures. These regions had slightly stronger gravity. Over billions of years, matter was pulled into these slightly denser regions. The dense regions became denser. The less dense regions became emptier. Over time, the tiny variations grew into the galaxies, galaxy clusters, and superclusters we see today. From these temperature maps, we can determine fundamental properties of the universe. The age, currently 13.8 billion years. The composition, about 5% normal matter, about 27% dark matter, and about 68% dark energy. The geometry of space, which appears to be flat, the rate of expansion. All of this from studying tiny temperature variations in ancient light. The cosmic microwave background is one of the most important pieces of evidence for the Big Bang. But when we try to understand the very beginning, the first moments, we run into problems.
Einstein's equations predict a singularity, but singularities are places where the theory breaks down. At the Planck time, about 10 to the minus 43 seconds after the Big Bang, quantum effects on spacetime should become important. Below this timescale, general relativity can't be trusted. We need a quantum theory of gravity, and we don't have one. The best we can do is patch the problem with a theory called cosmic inflation. Inflation was proposed in the early 1980s. The idea is that in the very early universe, there was a brief period when space expanded exponentially fast. In a tiny fraction of a second, the universe grew by a factor of at least 10 to the 26th. A region smaller than a proton inflated to the size of a grapefruit or larger. This solves several problems. It explains why the universe looks so uniform in all directions. It explains why space appears to be flat. And it explains the origin of structure. Quantum fluctuations during inflation would have been stretched to cosmic scales, creating the tiny density variations we see in the cosmic microwave background. Inflation is supported by observations. The patterns in the cosmic microwave background match the predictions of inflation. But inflation doesn't solve the singularity problem. It just pushes it back. Inflation requires very specific initial conditions, and if you trace inflation back far enough, you still reach a singularity where the equations break down. Some physicists have proposed alternatives. One idea is that the Big Bang wasn't the beginning. Maybe the universe bounced. Maybe it was contracting before the Big Bang and then bounced at a minimum size, transitioning from contraction to expansion. This would require quantum effects to stop the collapse before it reached a singularity. Another idea is that the universe didn't begin from a singularity at all, but emerged from nothing through a quantum process. Some models suggest the universe could have emerged from a quantum fluctuation of the vacuum, a spontaneous creation event allowed by quantum mechanics. But all of these ideas are speculative. We don't have a complete theory that describes the origin of the universe. We know the universe had a beginning. We know it was once incredibly hot and dense, but the very first moment, the nature of the beginning itself, is hidden behind a wall. Do black holes destroy information? The third big question brings us back to black holes and the information paradox. In quantum mechanics, information is never destroyed. It can be scrambled, spread out, hidden in complex ways, but it's always there in principle. This is called unitarity. But Hawking radiation seems to violate this. When a black hole evaporates, it emits thermal radiation that carries no information about what fell in. Thermal radiation is random, characterized only by temperature. If you collect all of the Hawking radiation from an evaporated black hole, you can't reconstruct what went in. The information is gone. To make this concrete, imagine you write a book and throw it into a black hole. The book has information, the specific arrangement of words on each page, the precise positions of all the atoms. The book crosses the event horizon and falls toward the singularity. From the outside, the black hole has gained a tiny bit of mass, but you can't tell what fell in. Now wait, the black hole slowly evaporates via Hawking radiation. After a very long time, the black hole disappears completely. All that's left is a cloud of random thermal radiation. Can you reconstruct the book from this radiation? According to Hawking's calculation, no, the information is lost. This creates a paradox. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and black holes don't actually destroy information, or both theories are incomplete. For decades, physicists debated this. Hawking argued that information really is lost. Others argued that information must be preserved somehow, that we just don't understand the mechanism. One key insight came from the holographic principle. This is the idea that all the information about what's inside a black hole is somehow encoded on its event horizon, the surface that marks the point of no return. The area of the event horizon is proportional to the black hole's entropy. This suggested that the information isn't lost inside, but is stored on the surface in a scrambled form. In recent years, there's been progress. The key breakthrough came from thinking more carefully about entanglement as a black hole evaporates. In 2019 and 2020, a series of papers introduced the concept of quantum extremal surfaces and islands. The idea is that when you calculate the entropy of the Hawking radiation, you need to include contributions not just from the radiation itself, but also from a region inside the black hole, an island that's correlated with the radiation. As the black hole evaporates, this island grows.
Eventually, it includes the entire interior. At this point, the radiation carries all the information that fell in. Information is conserved after all. Does this mean the information paradox is solved? Most physicists think we're very close, but there are still details to work out. The island calculation works in simplified models, but hasn't been fully proven for realistic black holes. But the progress is real. The black hole information paradox, which seemed like an unsolvable conflict, is yielding to new ideas, and those new ideas point towards something profound. Spacetime and gravity are not fundamental. They emerge from quantum entanglement. The fabric of spacetime is woven from quantum correlations. So why does all this matter? Understanding what spacetime is at the fundamental level would complete the picture of reality that physicists has been building for centuries. Right now, we have two great theories. General relativity describes gravity and the large-scale structure of the universe. Quantum mechanics describes particles and forces at small scales. Both are extraordinarily successful, but they can't both be right in their current forms because they contradict each other. A quantum theory of gravity would unify these two pillars of physics. It would give us a single, consistent framework for understanding the universe at all scales, and it would almost certainly reveal new physics, new phenomena we haven't imagined yet. History suggests that major unifications in physics lead to technological revolutions. A quantum theory of gravity could lead to technologies we can't even imagine right now. More importantly, understanding spacetime would answer some of the deepest questions humans have ever asked. Where did the universe come from? What happened before the Big Bang? Will the universe end? What happens inside a black hole? Why does time flow in one direction? These questions have fascinated humans for thousands of years. For most of history, they were in the realm of philosophy and religion. But now we're close. We have mathematical frameworks. We have observational data. A quantum theory of gravity could tell us what happened at the Big Bang. It could describe the interior of black holes. It could explain why time exists and why it flows forward. There's also something philosophically profound about the fact that space-time might not be fundamental. We experience space and time as the stage on which everything happens. The idea that they might be emergent challenges our deepest intuitions about existence. If space-time is emergent, then distance and duration might be illusions. At the deepest level, there might not be any space or time, just quantum information, and space and time emerge from the pattern of those correlations. We're living in a special time. We're the first generation to have the tools to probe these questions seriously. We have gravitational wave detectors. We have telescopes that can photograph black holes. We have particle accelerators. We have mathematical frameworks like string theory and loop quantum gravity. And we have brilliant physicists all over the world working on these problems. We might be close to a breakthrough,
or we might be decades away. But the fact that we're asking these questions is itself remarkable. So let's come back to where we started. Spacetime, Einstein's idea, the foundation of modern physics, an idea that's been tested thousands of times and has never failed, an idea we use every single day in GPS satellites, in our understanding of the cosmos, in the technology that surrounds us. And yet, the fundamental mystery remains. We don't know what it's made of. We don't know if it's fundamental or emergent. We don't know what happened at the Big Bang. We don't fully understand whether black holes preserve information, though we're getting close. This isn't a failure. This is where we are. This is the frontier of human knowledge. Every great idea in science eventually reaches a boundary where it can't go further without something new. And now we're at the boundary again. We're at the place where the smooth space-time of Einstein's theory meets the quantum world. Somewhere beyond that boundary is the answer, a quantum theory of gravity, a description of what space-time is at the Planck scale, an understanding of what happened at the beginning, maybe a unified theory, maybe something we haven't imagined yet. The physicists working on these problems today are standing at the edge, looking out into the unknown. They're using mathematics and creativity and centuries of knowledge to build bridges across the gap. And when someone finally figures out what space-time really is, it will change everything. So the next time you use GPS, or look at a photograph of a black hole, or think about the Big Bang, remember this: you're looking at one of the deepest mysteries in all of science. You're seeing evidence of something we use but don't fully understand. Space-time is real. We can measure it, we can photograph it, we can detect waves moving through it, but we don't know what it is. And that's where the adventure begins. That's where science happens, not in the answers we've already found, but in the questions we're still trying to answer. Einstein gave us the idea of space-time over 100 years ago. It revolutionized physics. It's been one of the most successful theories in history. But Einstein himself would probably be the first to admit it's not the end of the story. It's a step along the way, a beautiful step, but still just a step. The final answer is waiting. It's out there in the mathematics, in the experiments, in the observations yet to be made. Someone will find it, maybe in our lifetimes, maybe in the next generation, maybe centuries from now, but it's there. And when we find it, we'll look back at this time, this moment when we knew that space-time exists but didn't know what it was, and we'll see it as the turning point, the moment just before everything changed. As you drift off now, as your breathing slows and your thoughts begin to dissolve into dreams, carry this with you. The universe is full of mysteries. Space-time is just one of them, but it might be the most important one. The fabric that holds everything together, the stage on which reality unfolds, is itself a mystery. And somewhere in that mystery lies the key to understanding everything. If you enjoyed this journey through space-time and its mysteries, there's another peaceful exploration waiting for you right here on the channel. But for now, there's only rest, only the gentle pull of sleep, only dreams waiting in the dark. Good night, and may you dream of curved space-time, of ripples in the fabric of reality, of questions that lead to more questions, deeper and deeper into the beautiful unknown.